Notifications. Do not disturb. There we go. Hello there. Today let's discuss Zig and Rust and compare them side by side. But just a quick disclaimer, I personally use both Rust and Zig, and I don't think you should choose one over the other. Both languages are powerful enough that they can be used for any task. The question is how particular solutions are convenient or error-prone. In my opinion, Rust is still the better practical choice. But Zig is fun. It's a really pleasant language to use, and it has some niches where it shines. And this video is not an objective comparison. If you want to see something like this, let me know. But today, let's focus on only the parts where Zig shines. Okay, so 7 aspects in which I think Zig is better than Rust. Let's dive into the code. Let's say that we have a function returning a user by its ID, and we want the result to be an optional. Functions like this will do the job. It's already a bit different in signature and where we are returning the values. But even if I prefer the Zig version here, it's not a big deal. But now, let's say we want to use this function. To unwrap the value with a default value, we can use unwrap or. In Zig, it's or else. To unwrap the value or panic, we can use unwrap or expect. In Zig, it's the same or else keyword, now with @panic. To unwrap the value or to do something, there is unwrap underscore or underscore else method in Rust, which takes a function as an argument, and it's again or else in Zig. With unwrap or else, there's a problem. We cannot also change the control flow of the outside function, so we will need to use a special let else syntax in Rust here, or before it was introduced, we had to do pattern matching like this. And yeah, it's still simple or else in Zig. Also, something I use quite a lot, the unsafe method, unwrap checked. It will panic in debug mode and introduce undefined behavior in release mode. In Zig, it's again or else in combination with the unreachable keyword, which I will explain later, but the behavior is similar. Lastly, if we want to have an if statement doing something in case there is a value, in Rust we have if let syntax for that, like this. In Zig, there's also additional syntax for the plain if, but it's much cleaner. Okay, so by embedding optionals into the language, Zig is able to provide better usage ergonomics. There is a similar thing in error handling, but first, let's check another topic. Now, let me just quickly check what you said on Discord. Okay, you said you're quiet. Awesome. Okay, we're back. All right, let's talk about undefined behavior. Both languages aim for safety, but they approach uninitialized memory and possible code paths differently. One concept I find quite elegant in Zig is the undefined keyword. It represents a value that hasn't been initialized yet. Crucially, reading undefined is uncontrollable behavior, but assigning it is perfectly fine. This makes certain initialization patterns feel more direct compared to Rust. Let's look at an example. Suppose we want to initialize an array, but we need to fill it in a non-deterministic way. As we cannot explain it in terms of safe Rust, we will need to at least use some unsafe. First, we will declare our array as uninitialized using maybe uninit. Then we will fill the values using data provided by some iterator. Finally, we can write our unsafe block, not forgetting to explain why we are sure that all values are initialized, getting our array back to the i3216 type. It works and it's safe if you use unsafe correctly, but maybe uninit adds some verbosity for sure. Now let's see the equivalent in Zig. As in Rust, we declare our array using the undefined keyword. Then we initialize it in a loop, using the same iterator again, but this time we will need to access tuple values by field names. Right after that, we have our initialized array and we can use it. I still like to have a safety comment in Zig code, even if it's not a standard practice. But anyway, now related to uncontrollable behavior, it is the concept of telling the compiler something is impossible. Sometimes you know more than the compiler. For example, you might know that a particular error just cannot happen, or that an optional will always contain a value in a specific code path. Signaling this can allow the optimizer to generate better code. For example, let's check out this Rust code. Using the regex crate, we can create a regex pattern that captures a date. Since not every string is a valid regex pattern, calling new requires us to handle the error. Since the pattern is static and we know it will always be valid, we can use unwrap uncheck, hinting to the compiler that the regex will always be valid. In Zig, we can again use the or else keyword, but this time for the action in case the regex is invalid, we can say unreachable, which is an elegant way to signal to the compiler that this code path is impossible. There's another good use case for this. Consider we have some arithmetics in Rust, resulting in either 0, 1, or 2, and all other values are proven to be impossible. We could write a match statement like this. But since we have to handle every possible branch, we're marking the last one with unreachable, which is a macro that panics if the code path is reached. This will, again, generate extra code we don't need, and we can just tell the compiler that this is indeed unreachable, like, trust me bro, by using the unsafe hint unreachable unchecked. In Zig, we can use the same unreachable keyword. In release fast mode, it is equivalent to unreachable unchecked in release build in Rust, and is good for performance and code size. In debug and release safe modes, it will panic, which is similar to Rust's unreachable macro and is good for debugging. Okay, now let's talk about modules and how code is organized in projects. Rust's module system is not that bad, to be honest, but it can be quite confusing for newcomers, and I just find that Zig's solution is simpler and more intuitive. So in Rust, let's say you have a main.rs file where you want to call a function from another module. Let it be module A. In the function in module A, you want to call a helper function from module B. So now you will have 3 files, but before you can use both functions, you will need to let Rust know about the other files. To call the function from module A in main.rs, it's simple. Add mod module A to the top of main.rs. But now you want to call a function from module B in module A. Instead of adding mod module B to module A, you will need to add it again to main.rs again, regardless of where you're using it. Like, what? And we're not done yet, because inside module A, we also have to use the full path to call the function, or else it will not work. So it should be either create module B do more work at its call site, or use create module B at the top of the file. This style is pretty robust, even if it can be very confusing at first. But Zig uses a classic file/path-based approach for modules. Here's the same example with 3 files. First, to use a function from module A in main.zig, we need to import it first using the @import built-in. Then, to use a function from module B in module A, we do the same built-in in module A. For me, Zig's import based on file paths is just much simpler to understand and manage compared to Rust's declarations and potentially confusing path specifiers. It just feels more direct. Alright, let's look at how constants and variables are declared. This is another area where Zig feels a bit more streamlined to me, especially regarding mutability. So, local immutable bindings in Rust are declared using the let keyword. In Zig, we have to use the const keyword. For mutable bindings in Rust, we use the let keyword with the mute modifier. In Zig, this is different, where instead we have a separate var keyword. Now, this is where interesting things start to happen. For compile time constants, Rust has the const keyword, while Zig uses the same const keyword. In Zig, it doesn't force values to be compile time known, but we can do it using the Comptime block like this. Okay, so then there's another type to declare a global value in Rust, static. It defines an immutable global value, so it's like const, but this time with the value being actually in memory. So it's not just a compile time constant, but something existing at runtime. In Zig, we still use const at the top level, and it can be used both compile time, known or not, or being runtime accessible. And finally, we're here, where all the mutable global variables are. In Rust, we have let mutable, but that's only for local bindings. For global ones, we have to use static, again, with the mutable modifier. But accessing this global variable will be unsafe, so we have to use unsafe in order to read or write to it. In Zig, you will have to track safety yourself, but the declaration is simple. Since it's a mutable variable, it's var again, just declared at the top level. And that's it. Zig's approach is simpler, consistent, and I like it better. Let's talk about pointers. This is another area with significant differences in design, particularly around nullability. First, in Rust, you are not going to work with pointers. You will use references as a safe and convenient alternative. But sometimes you will need pointers. And if you do, you will agree with me that they are far from perfect. So for syntax, let's compare pointer declaration and dereferencing in both languages. So in Zig, pointers are mutable by default. So to declare a mutable pointer to an integer, it's *i32. And to declare a pointer to a constant integer, it's asterisk const i32. In Rust, it's also asterisk const i32 for a constant pointer, but for mutable ones, we'll have to specify the mute modifier explicitly, like this. Getting the address of a variable is the same in both languages using the ampersand operator like this. To dereference a pointer, Rust uses the classic asterisk operator like this, which is always unsafe, while Zig, for ergonomic reasons, uses the postfix dot asterisk operator. And in practice, it's great for chaining field access and dereferences like this. Okay, now after we've checked the syntax, there are important differences in how pointers work. In Rust, pointers can be unaligned. Moreover, pointer types do not encode alignment information, but they do in Zig. It's an advanced topic, and I probably will cover it in future videos on RAM, but in short, alignment is very important for performance and correctness of your code, and tracking it in a type system will save you from a lot of problems. Another thing that we can check here is that in Rust, pointers can be null by default, unlike references. In Zig, pointers are non-null and can only be null if you explicitly make their type optional. Again, this is a great thing to make code safer. In Rust, pointers can be wrapped with option non-null type, but that's going to bring a lot of problems outside of the scope of this video. So working with pointers is common in Zig, but easier, safer, and more powerful, while in Rust, you should be extra careful, considering that you will also have to track that you don't break the guarantees of safe Rust while using unsafe operations. I'm basically halfway done, but Comptime versus Proc macros is very long. Okay, next topic, Zig's Comptime versus Rust's Proc macros. These are not quite the same language concepts, so before I show you a direct comparison on a similar problem with real code, let me do a brief introduction. Both can be used to do some type of compile time calculation, or code generation. Both use the same language instead of something like a separate macro processor, and they're both great at reducing boilerplate. And since they're both Turing complete, we're having the halting problem at compile time in both. Yay! Woohoo! Alright, so what's different? First, Rust's proc macros operate on token streams and provide an AST representation. In Zig, comp time is just Zig code being interpreted during the compilation step. Because of this, Zig's comp time is quite easy to use and understand, while Rust's proc macros are very hard to create. By the same reason, Rust's proc macros allow us to implement any custom syntax and generate almost any valid ASTs, while Zig's comptime only accepts compile time known values and returns them, but types are first-class objects in Zig too. Again, by the same reason, Rust proc macros cannot get semantic information about their input, while in Zig, we can do full-powered compile time reflections and quite easily. Also, Rust proc macros may not be used from the crate where they are defined from, and can only be used when imported into another crate, while in Zig, you can even call a comptime function recursively. And finally, because Zig's comptime functions can work with types, they can also be used to create generic types, while in Rust this is not possible for proc macros and a different mechanism is used for generics. Okay, so now that we know what comptime and proc macros are, let's solve a problem suitable for both. Imagine we have an embedded CSV file in our program and we want to generate a struct based on this CSV header. For example, for a file like this, it should generate a struct like this in Rust, and a struct like this in Zig. So, with proc macros, we cannot directly return a new struct, but we can modify an existing empty one with an attribute, so the usage code will look like this. But it's already better in Zig. We can just define it as a result of a function call like this. Yeah, but the real difference is how we implement this macro and function. Let's see Rust's implementation first. Here is the file structure. Due to the limitation of proc macros, we have two crates here, one for the macro and another for the actual program. In the crate for the proc macro, we also need to specify the dependency on proc macro as it's a requirement to implement it, and on the syn and quote crates, since they simplify macro creation a lot. In main RS, usage is as we showed before, and the macro crate is included like this. So let's see librs with the implementation. First, we will have some useful use statements. Then comes our attribute macro, CSV struct. Here, we're parsing our first input, the path to the CSV file, using parse macro input from syn. That's why we're using the syn crate. Otherwise, we would have to write the parsing manually. Then we're getting the full path to the CSV file starting from cargo manifest dir. After that, we're reading the file content and getting the last line. Now, splitting it into field names. We should probably process them here, but let's try to keep things simple. Then, since we're modifying an existing struct, let's get its visibility modifier and name. And finally, let's build the final structure. Here, we're going to use quote magic. It simplifies some things for us. We don't have to build the resulting token stream by token, but the cost for that is another level of abstraction and magic. Okay, anyway, our solution is ready. Let's see the Zig one. File tree is simpler, and it's all done in a single Zig project now. Usage is, again, as I showed you before. Let's see the implementation. First, we define a regular function, getting a path to the CSV file and returning a type, our struct. Inside the function, we're reading a CSV file and getting its header. Then we're splitting the header into field names. And now we need to create actual field definitions for their names. And it's quite simple. Just this. We have to choose a lot of things here, but it's the entire field definition and it's just a struct in Zig. Finally, once we have our fields, we can create and return our struct definition. And it's, once again, just a struct in Zig. Except for some low-level details, I like the Zig solution to this problem way more. It doesn't require a separate crate. The signature of the function clearly says what's going to happen. And instead of quote magic or manually building a token list, we're working with simple structures representing our types. In the case of another problem, if we need to take multiple existing structs as parameters, for example, to create a third merge struct, we couldn't use Rust macros at all, while in Zig, the code will look quite similar. Get two types as arguments, return another type, and in the body, collect types from both structures and put them into our result. Even simpler than creating a struct from a CSV header. One more thing. In my experience, Zig often feels way simpler than Rust when it comes to seamless C interop. For example, let's say we want to use a C library in Rust. We can link it with our Rust project, but we cannot directly call C functions, so we need to write bindings ourselves or run bindgen to generate them. The usual practical approach involves a few steps, often managed in a build.rs file. First, it needs to build the C library so we can link it. Then it typically runs bindgen to generate the Rust bindings from the C headers. In cargo.toml, we need to specify that our crate has this custom build process. We also need to add the necessary build dependencies, like bindgen itself. And finally, we can include the generated bindings in our code, usually like this. Extra sweet point, bindgen marks all generated wrappers as unsafe because Rust cannot guarantee C code safety. This means that we usually need to write safe Rust abstractions on top of this. For now, let's just use the necessary unsafe keyword. Now in Zig, things can be simpler. You can tell Zig about the C library in your build.zig file. But since Zig is also a C compiler, it can just build the C code without an extra dependency. And crucially, because Zig can use C headers directly via @c_import, we can just include them directly like this. This is a huge difference in ergonomics.
Hi guys, it's me now, codingjerk. I just noticed that I don't like this part on post-production, so I decided to re-record it. Alright, so quality of life improvements in Zig over Rust. In Zig, I like unit tests more. They are more compact, they are cleaner, they are easier to write, and you can return the error without declaring the type. Another one, while it's not easy to make a memory leak in Rust, believe me or not, it is safe to do so. So to debug memory leaks in Rust, we will need to use a separate tool like Valgrind. In Zig, due to the powerful allocator system, we can enable memory leak detection in the general purpose allocator for our test or for the whole program for debug builds, for release builds, you choose it. Also, in Zig we have many extra pointer types. It makes a separation between a pointer to a single value and a pointer to multiple values. Then there is a slice, aka fat pointer, and a pointer to a static array. It also has great integration for zero-terminated pointers or static arrays or slices, which is awesome for C interop. Okay, that was my part. See you guys. I'm giving the mic back.
And finally, allocators. While Rust has the allocator API in Nightly, It was put into the language as an afterthought, and controllable allocations, arenas, and other things in Zig are just better. Alright, that's it for today. Again, this video was voiced by me, Tokisuno. Check out my channel in the description. Subscribe for more content like this, and I will see you in the next video.